the Department of Computer Science, the University of Warwick. He did his PhD Theoretical and Mathematical Physics from the University of Cambridge, and before that, he did his bachelor's from IISc. His research focuses on quantum algorithms and complexity theory. Today, he'll be talking about quantum worst case to average case reductions for all linear problems. With this, I hand over to him.
Am I audible? No. Okay, so okay, that's. Okay, is this any better? Can you hear me? Okay, no, this is not on. Is this okay? Just further up.
Maybe if you're in the back, you can say.
Yeah, can you hear me? Is this okay? So it's still not. I'm still not audible. It is better. Okay. Should I pull this further up? Am I audible at the back? Okay, great. So maybe I can also just speak a little bit louder. Thanks to everyone for coming to this talk, and thanks to the organizers for having me. I think this is a great seminar series. And as advertised, I'm going to talk about worst case to average case reductions for linear problems. And in particular, I'm going to talk about quantum algorithms. So this is quantum worst case to average case reductions. This is joint work with Wahid Asadi at the University of Waterloo, Alexander Golovnev at Georgetown, Tom Gore at Warwick, and Igor Shankar at the Simon Fraser University. Okay, so without further ado, I'll get straight into the topic. So just to explain what the title means to begin with, I'll start off by saying what I mean by an average case algorithm. So a classical average case algorithm is one that, suppose it's an algorithm that's meant to compute some function from some finite field f, some vector space of dimension n over a finite field f, to a similar vector space. If alg is randomized, then what I mean by an average case algorithm is one that has this property. And what is this property saying? So with some probability over the internal randomness of alg is going to compute the right answer. So f of v is the correct answer that we want on any input v. And with some probability over the internal randomness of the algorithm, it's going to compute that answer. And now if we take the expectation of this success probability as we treat the success probability as a random variable and take its expectation over a uniform random input from the domain of f. And if we ask for that quantity to be larger than alpha, so if it's bounded away from 0, if it's larger than alpha, I call this an alpha average case algorithm for computing f. So effectively what this means is that alg is randomized, so it doesn't succeed always. And if you draw a typical instance, if you draw a uniform random instance of the problem, then alg succeeds with some appreciable probability, some non-trivial probability. Okay, so this, yes.
Rather like satisfiability instances with the inherent probability are never satisfied.
Yeah, that's true. We're interested in certain classes of problems where alpha. I'll come to that in a bit. So we can deal with alpha being sub-constant in a lot of cases, but how far sub-constant is a question that's not that's still open. But we can deal with sub-constant alpha. Okay, so and speaking of which, please feel free to interrupt and ask questions if something is unclear. Okay, so the second thing that I need to explain before going into the actual talk is quantum algorithms. So
just take stepping back. So the typical is it's not a point-wise, like a much better, more standard guarantee would be that the green expression is at least alpha for all v.
Right, that is a much stronger assumption, right?
That's the worst case.
Yeah, that's a worst case assumption. And here what I want is, I start with an average case algorithm, and I want to get to a worst case algorithm. So in fact, what you just pointed out is the goal of the work. The goal of the work is to knock off this expectation here and get the condition that you just mentioned. Okay, so The second thing that I need to introduce is quantum algorithms. So I'll just give a very brief sort of 3-slide overview. So quantum mechanics is really just linear algebra over the complex numbers plus 4 postulates that connect physics to the maths. And these 4 postulates essentially establish an L2 probability theory. And I'll say what I mean by an L2 probability theory. So the 4 postulates are, you can take different sets of postulates, but I'll pick one set that I'll explain here. So the first one is, I'm loosely calling it superposition. What I mean is, or rather, what this postulate says is that an n-dimensional quantum system can be, it's like, so when we think about Turing machines or devices like that, they have states that they can be in. So similarly, a quantum computer, an n-dimensional quantum computer, can have states that it exists in. And these states are going to be vectors. They're going to be complex vectors in the n-dimensional complex vector space. And subject to the condition that their L2 norm is 1. So they're normalized, they have unit L2 norm. And an example is the qubit. So a qubit is a 2-level system. It's the state of a qubit. The states that a qubit can exist in are vectors in C2. So in this case, this vector has components alpha and beta in the standard basis, so the 1, 0, 0, 1 basis. And the L2 normalization condition reduces to, because these are complex numbers, this is the absolute value of alpha squared plus the absolute value of beta squared. And this is where the popular sort of description of qubits comes from. So because this is in the standard basis 1, 0, 0, 1, if we interpret 1, 0 as the binary 0 and 0, 1 as the binary 1, then this is sort of saying that the qubit can exist in a mixture of 0 and 1 states. So unlike a classical bit, which is either 0 or 1, a qubit can exist in a mixture of 0 and 1 states. The second postulate, and one of the most important ones, is measurement. So one of the operations that a quantum computer can perform is a measurement. It can take a state, it can be in a state, and it can perform an operation called a measurement. What does a measurement do? It takes a state V and an orthonormal basis for this vector space Cn. So it could be any orthonormal basis. And the output of this measurement operation is one of the labels here. So it's one of the labels B1 up to Bn. And which label is output is subject to this condition. So the label Bi is output with probability given by the overlap of the state B with the vector Bi, with the basis vector Bi. And putting these two together, you can see that if I take a qubit that is in the state, let's say alpha and beta are both 1 over square root of 2, which means that alpha squared and beta squared will both be half. What that means is that if I take a qubit in that state and I measure it, it can give me a classical bit 0 or bit 1 with uniform probability. So that's the measurement postulate. The third and fourth postulates are evolution and entanglement. Entanglement is not really, this is not a postulate, I'm being sort of loose here, but these are the properties that will be important. So evolution, so how does a quantum state evolve? So in classical computer science, with Turing machines, we have transition functions, we have things that describe how the machine progresses from one state to another. So similarly, a quantum computer can be in a state V, and it can evolve to another state V prime via unitary maps. So unitary maps means that these are just linear maps over this vector space. So in principle, in particular, you can think of them as matrices, n by n matrices. And these matrices have to satisfy this condition, where this simple dagger means that I take the complex conjugate and the transpose. So these are unitary maps, and any evolution implemented by a quantum computer is represented by a unitary map. So if you start in a state V and you want to end up in another state V prime, the computer has to have performed some unitary map that takes V to V prime. And entanglement is a curious feature that arises when we think about multiple quantum systems. So classically, if you have multiple bits, then the state of those multiple bits is described by the Cartesian product of 0, 1, so bit strings. But if you have multiple qubits, then their states are no longer described by Cartesian products, but by tensor products. So here, if I have 3 qubits, all starting in the 1, 0 state, then the composite system has a description that's given by this 8-dimensional vector. And these red numbers here are just the indices. So you can associate these, because this is an 8-dimensional complex vector space, you can associate these coordinates here with basis vectors. So when you think about measurements, there should be 8 basis vectors for an 8-dimensional space. So you can think of these as labeling those basis vectors. And so to connect back to measurement, if I measured this composite system, if I measured all the 3 qubits of this composite system, then I would see the output 0, 0, 0 with probability 1. Because here alpha in this sort of notation, alpha is 1 and all the other components are 0 here. So all you'll see when you measure is 0, 0, 0 with certainty. So with these postulates in mind, this won't really be all that important for the talk. I just wanted to set the stage. Right, so before going into other details, a quantum algorithm in general looks like this. At least for the purpose of this talk, we're just interested in the circuit model. So a quantum algorithm is a unitary. As I said before, you start in some state, you want to evolve to some final state. So the initial state encodes your problem instance. The final state encodes the answer to the problem. And you want an algorithm that takes you from the initial state to the final state. And to study the complexity of quantum algorithms, you need to fix some model, some measure of complexity. And the one that we'll be interested in is circuit complexity. The quantum circuit complexity that we're interested in is the following. So a unitary circuit, a unitary algorithm, can be written as a product of 2-qubit gates. So smaller, because every algorithm is a unitary map of this form, and that's a matrix. I can now think of taking an arbitrary n by n matrix and then splitting it up into a product of smaller block matrices. And these block matrices act non-trivially only on 2 qubits at a time. So if we count the number of 2-qubit gates inside this unitary, the minimum number of 2-qubit gates required to implement a certain unitary is a measure of complexity for that algorithm, for that problem. And this is the notion of complexity that will be important for this talk. To recap, there are 3 ingredients in a quantum algorithm. There are the qubits, which encode the data, which encode the problem instance, and at the end, they will also encode the answer. Then there's the evolution, which is the transitions and all the computation that's performed by the quantum computer. And this is represented in the form of a circuit, a product of 2-qubit gates. And these gates, when I use the word gates, that's exactly analogous to classical gates. So this is analogous to and or not gates, except there are a lot more of them. No, this is just the matrix product. Okay. Yeah, just the product of operators. And the third important component is measurements. So the algorithm takes an input, applies some evolution to the input, and then measures all the qubits. And that measurement gives some classical bit string as output. This classical bit string now has to be interpreted as the solution to the problem. Okay, so there are 2 tasks where quantum algorithms excel, like distilling all the sort of 30 years of research in quantum algorithms. There are 2 primary areas where quantum algorithms excel. One is finding subgroup structure. And Shor's factoring algorithm is an example of this. So Shor's factoring algorithm belongs to a larger class of algorithms called the hidden subgroup problem algorithms. And essentially what they do is to find a subgroup structure that's hidden in some function. And the second thing that they're very good at is Markov chains, rapid mixing of Markov chains. So this is essentially Grover search. So unstructured database search is what the original title of the paper was. But this is more generally interpreted as mixing of Markov chains. So if you have a classical classical Markov chain that has a mixing time t, then you can lift this to a quantum algorithm, a quantum process that has mixing time square root of t. So you mix much faster. And most quantum algorithms to date are in one way or another, they're related to one of these 2 things. So that the main technical ingredients that most quantum algorithms to date use distribution. Yeah.
Easy to see that.
based in terms of mixing of Markov chains.
It's for explicit Markov chains or even for like it's like volumetric things, convex body, volumetric.
Okay, I'm not very familiar with that, but it is possible to do this for some implicit problems because the input that's required is not really an explicit description of the problem. It can be done in a lot of oracular models. So I think it might fit the problem that you're talking about, but I'm not familiar with that problem. Okay, so shall I move on? Okay. Okay, right. So having described what quantum algorithms are roughly like, I want to describe what the quantum analog of an average case algorithm should look like. And this is still the same. So you take an expectation over a typical input. And this is just a change of notation. You don't really need to take this too seriously. So as I mentioned before, the input is now represented as a quantum state. So the V here represents the input. The 0 here represents additional workspace that the algorithm could take. Alg is now a unitary. It's a unitary operator that's being applied to this state. So it evolves it into some other state B prime, comma B prime in the first register and W prime in the second register, some work that the computer has done. And this projection here represents the measurement that's done at the end of the process. So the subscript FV here says that I'm performing a measurement and I'm looking at the probability of seeing f of v as the bit string that comes out at the end. So just to go back here, what the algorithm does is it performs some evolution and it performs measurements, and the measurement gives a classical bit string as output. So I want the classical bit string that's output by the algorithm to be fv, because that's the condition that goes in here. And that's what this pi subscript fv represents. And there's this norm squared that appears here because, as I mentioned before, this is an L2 probability theory. So the outputs are the output of a measurement is bi with probability absolute value of b in a product bi squared. So that's why the squared appears here. Right. Again, this is not really going to be so important for the talk. I'm going to be focusing on the more high-level conceptual details rather than the intricacies of the quantum parts of it. But just to get the definition of the main objects in the title out of the way, this is what I mean by an average case quantum algorithm. For a function f from an n-dimensional vector space over f to the same space, a quantum average case algorithm with success probability or rate alpha satisfies this condition.
Does the circuit complexity is also related to the depth of the circuit? At some point,
Okay, right. So the circuit complexity, the depth is one of the measures that we're interested in, but we're also interested in the size of the circuit. To compare to classical circuit complexity, the size of the circuit is more important in the quantum setting because it also has relations to the time complexity. But the depth is also an important parameter, yes. In this talk, I will mostly be interested only in the size of the circuit, not so much in the depth. Okay, so.
It's important for everything to have output that is not binary, but
Right, no, it's not important. So our algorithm works for all fields, so it also works for large fields and as well as for small fields. I'm sorry, does that answer? You can think of everything as being, mapped down to binary, yeah. Okay, so what are some examples of average case algorithms? Like, where do they come from? So a simple example is for whatever problem you have, some third party that knows how to compute the answer could just compute the answer and then flip a coin with bias alpha. And if the coin comes up heads, then it can output the right answer, the answer that it computed. And if it comes tails, then it can just say I failed. So a third party can do this to you. And this would behave like an average case algorithm from your point of view. Another example is a deterministic algorithm that computes the correct answer on some small but highly structured subset of instances. So it could be the case that maybe, I don't know, you're trying to invert Toeplitz matrices or something like this, and you can come up with efficient algorithms for that subclass of matrices, but it fails on other inputs. This would also constitute an average case algorithm if the set of inputs on which the algorithm succeeds has density alpha. Okay. Why is this bad? Like, why are we not happy with just having average case algorithms? And then, why do we need to worry about worst case algorithms? An average case algorithm might never succeed on some inputs. So as is made obvious in the second example here, a deterministic algorithm that succeeds only on this subset X obviously fails outside X. And so the average case condition that the algorithm satisfies is very weak. So it might fail on most inputs. It succeeds on some small fraction of inputs, some small fraction of typical looking inputs, but it fails on crucial instances. Okay, so in this talk, the question that occupies us is, can we still use ALG? Can we still use an average case algorithm to solve worst case instances? That is, given an arbitrary instance of the problem, can I somehow use ALG as a black box, maybe perform a Turing reduction to different instances of the original problem and plug those into ALG, somehow combine the outputs and solve an arbitrary worst case instance? That is the theme of this work. So why should we be interested in this kind of reduction? So I did say why average case algorithms are not satisfactory enough, why we want worst case algorithms. But there are more reasons why reductions by themselves, these objects, the objects that reduce from worst case instances to average case instances, are interesting in their own right. And there are two primary reasons that I'd like to focus on. So one is that if we can reduce from worst case to average case instances with some conditions on the complexity. So the reduction itself should not solve the problem. The reduction itself, so we're operating in the regime of fine-grained complexity. The reduction should be reasonable. It should not take too much resources. If that is the case, then this gives us a way to design worst case algorithms by designing average case algorithms. So average case algorithms might be easier to come up with in some settings, such as what I said on the previous slide. So if you can solve problems on a highly structured subset of instances, like Toeplitz matrices or upper triangular matrices or something, you can design an average case algorithm. If that average case algorithm has a high enough rate, if the alpha associated with it is large enough, then I can plug in that algorithm to the reduction and get a worst case algorithm. So this is an optimistic reason to be interested in reductions of this kind. On the other hand, these reductions also let you prove lower bounds for average case algorithms. So it lets you prove average case hardness results. So I can take a problem for which I know a lower bound in the worst case. If there is a reduction in fine-grained complexity that uses a reasonable amount of resources, then the existence of a reduction from worst case to average case for that problem implies that the worst case lower bound carries over to the average case. So this average case lower bounds are, in a sense, a lot stronger than worst case lower bounds, in the sense that even if you draw a random instance and only ask for the algorithm to be correct on a random instance, not on all instances, there is still a lower bound on the amount of resources that it has to use. So these are two reasons why we're interested in these reductions. Okay, so I'll start getting into more of the technical details now. So our main result is the following. So if you're given a unitary quantum algorithm, ALG, for a linear problem. So I'll come to what I mean by a linear problem. For a linear problem M, and that can solve, let's say, alpha equals 1% of the inputs, then we can construct a new algorithm, ALG prime, for M, using with overhead n to the 3 halves, that scales as n to the 3 halves in gate complexity, in circuit complexity, such that ALG prime can solve all instances of the problem. And the n to the 3 halves here is important, and that'll become clear when I explain what I mean by linear problems. So as I mentioned before, the alpha here, our methods can actually deal with alpha that is subconstant. So with our current bounds, we can deal with alpha that is inverse polynomial. There are stronger methods that can deal with inverse quasi-polynomial alpha. Sorry, did you have a question?
It sounds a bit paradoxical compared an example. So we have a deterministic algorithm that works on alpha fraction and absolutely fails on the other.
Yeah.
How are you going to claim that you can convert it into a...
Yeah, exactly.
Work for 100% of all these?
Yes. Yes, it is very counterintuitive. So a priori, there is no reason to believe that it is even possible, but it turns out to be possible to construct such reductions. Yes. Yeah, good question. So there's an overhead that depends on alpha here, and that's why I fixed alpha to be 1% because I didn't want to complicate things with the alpha dependence. The alpha dependence is inverse polynomial.
There's something crucial about the polynomial has to do with linear.
Yeah, certainly. In the classical setting for worst case to average case reductions, we know how to perform these reductions for some specific problems. So for example, for matrix multiplication, we know how to reduce from worst case instances of matrix multiplication to average case instances of matrix multiplication. The nice thing that we can do in the quantum setting is that for all linear problems, we can do this, not just for specific problems such as matrix multiplication, but for any linear. Okay, again, I have to explain what linear problems are. I'm sorry that this is a little bit non-linear. But yes, the fact that this is for linear problems is crucial. And in contrast, in the classical setting, we do not know how to reduce worst case instances of linear problems to average case instances. Okay, so
the theorem as stated is constructive in the sense that you will give me alpha prime.
Yes.
Not an existential.
No. We explicitly construct the reduction and alpha prime.
And that construction itself, the efficiency of that is.
Yes, that is this overhead. It's the overhead of the reduction that I list here.
It's not like alpha prime uses these many more gates than alpha. It's the.
Right. Yeah, because it's a Turing reduction. It's a Cook reduction. So it uses. Alpha prime uses alg a few times. Alpha prime uses alg a number of times that depends on alpha. And because I set alpha to 1% here, I dropped it from here. The dependence is 1 over alpha to the 5. So alpha prime uses alg 1 over alpha to the 5 times as a black box. In addition, it uses n to the 3 halves, a circuit of size n to the 3 halves. Yeah.
In the classical case, if you want to achieve this, then additional gates to the power n or something is known or nothing is known.
So for the classical case, okay. So for linear problems, yeah, maybe what I should do is to go to what I mean by linear problems. Before that, I'll just make a small remark, which might not be so important. The model of quantum algorithms that our thing works for, it works for uniform circuits. So it works for circuit complexity. It also works for query complexity. Quantum query complexity is the analog of classical decision tree complexity. Okay, that's just a minor point. Right. So what do I mean by linear problems? Yes. Sorry?
Previous slide.
Oh, yeah.
Average case algorithms mean that expectation of probability is greater than alpha.
Yes.
And for worst case, we drop the probability of every.
Yes, for every instance, there should be a non-zero success probability.
So here, by the second statement, you mean that for 100% of the inputs, for every input,
yeah,
you succeed with at least alpha probability.
Okay, good question. So if you want to succeed on every instance with probability 1 minus delta, you can do that. So if you want to fix an additional, success, you want to boost the success probability to 1 minus delta, you can do that, and there will be a dependence on delta. It's a very weak dependence. It's a dependence that is polylogarithmic in 1 over delta.
So basically, these things are high probability.
Yes. Yeah.
It's a standard boosting.
It's a standard boosting. Yeah. Okay, thanks. So linear problems. What I mean by linear problems is the following. So there is a family of matrices that's fixed beforehand. The input is a vector, and the output is the matrix vector product. I think to answer your question, there is a trivial upper bound on solving this problem. So if we're thinking about square matrices, then with a circuit of size n squared, you can always solve this problem. So in the classical case, we do have reductions. So that's actually a great question, which brings me to one of the subtle details of our work, which is that we work in the setting of fine-grained complexity. So all our reductions, whether the reductions make any sense at all, depends crucially on their overhead. The overhead has to be. It's not just enough that the reduction is a polynomial time reduction or a reduction that has gate complexity polynomial in n. It is crucial for the reduction to have gate complexity that is little o of whatever appears here.
Sorry, I didn't understand the family of matrices.
Yes, yeah.
And output is n times v for one particular matrix from that or for all?
Okay, so the family is indexed by n, so it's like for each dimension. Yeah. I think it'll be clearer if I give an example. So a classic example would be the discrete Fourier transform. So discrete Fourier transform on size n. You know the matrix. The matrix can be specified locally very efficiently. This is known to the algorithm, and you want to compute the the Fourier transform of some input vector, you want to apply that matrix to the vector. So that's the standard example. Yeah, the problem is essentially matrix vector multiplication, and you can do polynomial evaluation in this model because the matrix, the family of matrices, would be the van der Waals matrices. The input would be the coefficient vector of the polynomial. You can also solve systems of equations over finite fields. There are relations to codes. So that's why linear problems are interesting. That's why we're looking. So we're looking at linear problems for two reasons. One is that they're interesting, and two is that there is a surprising thing that happens, which is we don't know how to construct worst case to average case reductions for linear problems classically, but we were able to do this in the quantum setting. Okay.
Can you speak on how MS is the family is represented? It's not a P/polynomial.
Uniformly given family.
Yeah, exactly. So that is again a great question. This is related to my little comment here about uniform circuits of query complexity. So our reductions work in the uniform model. They also work if you have query access to the family of matrices. Okay, so is everything clear so far?
So without any reductions, is there a lower? You said there's a trivial order.
Right. Right. So is there a trivial lower bound? In the classical setting, there is a lower bound of n squared. Yeah. Classically, it is just theta of n squared. Quantumly, there is no trivial lower. I mean, the trivial lower bound is just linear, so we don't have a good lower bound. Okay. So one of the main tools that we use to construct our reductions comes from additive combinatorics. So I'll spend a few slides to go over what tools we're using. So additive combinatorics is the study of approximate notions of algebraic structure. So you want to start with some very weakly structured set. It's not going to be a group or anything of that sort. It's just going to be some weakly structured set with maybe addition defined on it. And we want to study analogs of the notions that we study in algebra. So, the notion of subgroups or normal subgroups and things like that. And the techniques that we use to do this come from number theory, combinatorics, and Fourier analysis. So one thing that will be important for us in this talk is what's called the sum set of a set X. So if I start with some large set U and then X is a subset of U, the sum set X plus X, the sum set of order 2, is the set of all elements X1 plus X2. So it's the set of all possible sums of two elements from X that you can form. And more generally, the sum set of order T is the set of all sums of up to T elements from the set. And these things sort of give you a way to analyze combinatorial analogs of subgroup structure. So a key example to illustrate that intuition is that if X plus X was equal to X, that is the analog of a subgroup. So if you had a group G and a subgroup H, the defining feature of a group is that it's closed under the group operation. So the subgroup H is closed under whatever the group operation dot is. So H dot H will be H itself. And if X here had a sum set of order 2 that was equal to itself, then it behaves sort of like a subgroup would in algebra. More generally, if you look at the sequence of all sum sets and they converge somewhere instead of converging to the entire set, then that is, in some sense, approximately a subgroup. It behaves approximately like a subgroup. So this is just sort of a broad overview. And the specific tools that we use from additive combinatorics, I'll come to that in a second. So I'll now go into the high-level approach for proving the theorem that I wrote down a few slides ago. And that approach is local correction. So this little blurb here, it's meant to show that what we get is now a bad instance. So the algorithm is not very good. It only works on some instances. We now get a bad instance, and we want to solve it. We're going to break it up into a bunch of instances. We're somehow going to combine what Al can do on the good instances, and then do some stuff, and then solve the instance X. And I call that local correction because we break down a bad instance. We break down the computation on a bad instance into computations on a small number of good instances. Okay. So to sort of give you some intuition for how this works, suppose we have the following condition. So here, I've dropped the expectation here because I want to focus on the second example that I gave of an average case algorithm, which is ALG is now a deterministic algorithm. It succeeds on alpha fraction of its inputs. So I can drop the green success probability because ALG either succeeds or fails. And the expectation outside is just now the probability over V. So suppose we have an average case algorithm that's really, really good. So it succeeds on 99% of the inputs. Then there's this famous paper from 1990, Bloom, Luby, and Rubenfeld. The idea is what they call linear local correction. So what you do is to sample a random vector, a uniform random vector from the domain, split up your arbitrary. So V is now a new instance. V is a worst case instance that comes as input to the algorithm. You split V up into R plus V minus R. Now R and V minus R are both uniform random. Then if you computed V prime, which is the output of ALG on R plus the output of ALG on V minus R, because this is a linear problem, so this is where linearity becomes important. Because this is a linear problem, V prime is going to be equal to the true solution with this success probability, which comes from asking for both of these to be correct. And so you can see that just by doing this very simple algorithm, this very simple reduction, you can make you can get this new algorithm ALG prime that works on all instances with probability 0.9. One thing to note here is that this only works if alpha is at least 3/4. If alpha is because we have a union bound going on here. If alpha is less than 3/4, then, or in fact, even if alpha is equal to 3/4, this doesn't make, we can't apply the union bound anymore. This doesn't make sense anymore. So in the high agreement regime, we have this simple linear local correction algorithm. And what we're interested in is asking how we can push this further. How can we push this to the low agreement regime? So forget alpha being subconstant. How do we even push it to alpha being 3/4 minus epsilon? So as I mentioned on the previous slide already, this breaks down if alpha is small. So this is meant to say alpha is 1% rather than 99%. And an example to show that the technique on the previous slide breaks down, you don't have to just take my word for it. So here's an explicit example. So suppose we're just working over F2, and suppose the average case algorithm is defined as follows. So if the first coordinate of the input is 0, then ALG outputs the correct answer. If the otherwise, ALG just outputs the all zeros vector. So this algorithm is correct at least 50% of the time. Alpha is larger than 0.5. But if we use the idea on the previous slide, so if we use this linear local correction idea, we sample a uniform random vector and break the input up into R plus V minus R. For any instance that has 1 in the first coordinate, a linear combination of, if we break it up into a linear combination of 2 vectors, there is necessarily going to be 1 vector that has 1 in the first coordinate. And ALG is necessarily going to be wrong on that input. So the linear local correction idea doesn't work, even if alpha is 0.5. Okay, so what do we do?
Easy fix.
Yeah, what would you say it is?
Keep the first coordinate fixed and like randomly partition.
Keep the first coordinate fixed and.
If it's 1,
Yeah.
if it's 0 already, you're done.
Yeah.
If it's 1, then break it up. Okay.
Yeah, it is. I think it is in fact not possible to make it work.
Okay.
Yeah. So that's where additive combinatorics comes to the rescue, and in particular, the result that we use is the following. So if you have some subset X of the of this vector space Fn, X is just an arbitrary subset. It has no structure, and suppose X has density alpha. Then there's this result called Bogoliubov's lemma, which asserts that there exists a linear subspace V in the sumset of order 4 of X. And in addition, Bogoliubov asserts that the dimension of this linear subspace is very large. In fact, it's almost the entire space. It's n minus, the dimension is n minus 1 over alpha squared. And the alpha, that's where the density enters the picture. So in the end, it's this 1 over alpha squared that will give rise to factors in the complexity as well. But it's this surprising result that we use for our reductions. Okay. So Bogoliubov's lemma is sort of like pulling a rabbit out of the hat, because you start with a set X that has no structure at all. It could be just points sprinkled all over the space. And what you get out of it is a subspace. A subspace is a highly structured object. It's a hyperplane in the space. So the key idea that we're going to use is let's use this subspace for local correction. So we start with that's a great question. That's half of our work. It's not in the additive combinatorics literature. It is semi-constructive. And we have to show that we can actually construct it within the complexity limits that we're allowed. Okay. So
you are assuming X has its additive limit, or something like that has to be there, right? Otherwise, I can pick an X as it 4X does not have the all zeros vector, and in which case there is no subspace. Something has to be set, like you have to have the all zeros vector within 4X for it to admit any subspace.
Right. So in fact, I think that is exactly why this is a surprising result. You don't need any additional conditions. The only condition you need is that you don't need any conditions. You just need a subset X. If its density is alpha, then you have a subspace of dimension n minus 1 over alpha squared.
Do this in anything less than 4.
Okay, so you can do it with 3. If you do it with 3, you get an affine subspace. So this is probably related to your question, actually. So if you looked at the subspace, if you looked at the subset of order 3, then you can prove an analogous result, which asserts that you have an affine subspace, which will not contain 0. And for 2, it's still an open problem. The case of the subset of order 2 is not fully understood yet. Okay, so how do we connect this result to worst case to average case reductions? So we want to do local correction.
The density of X.
Yeah.
And the dimension, does that play any role? Like how does the alpha somehow play a role in getting the 0 vector?
Right. No, I think it doesn't. So it's the number here that plays some role in getting the 0 vector, because if you make this 3, then you can't prove that you get the 0 vector always. But as soon as it's 4, you do get the 0 vector. Okay. Are there any further questions? Okay. So the idea is that, so you can see that there's a 4x here. So we're going to sort of, earlier we were decomposing the input into 2 pieces. You can sort of imagine that here we're going to decompose an arbitrary input into 4 pieces. But before we go there, the condition that we have, the input algorithm satisfies this condition, which is that on average over, it's a deterministic algorithm, so on average over random inputs, it succeeds with probability alpha. And suppose we consider the set of vectors on which alg succeeds with probability at least alpha over 2. Then by Markov's inequality, this subset has density at least alpha over 2. So you can see that this is starting to look like that. So if we now plug this subset, so given an algorithm that satisfies this condition, we're guaranteed that there exists a subset of density alpha over 2. This is, at this point, this is not explicit at all. This is just an existential statement. There exists a subset that has this property. And I'll call this the set of good inputs for alg. We want to plug this subset into Bogoliubov's lemma. So the sum set of order 4 of this subset, which we don't know yet, is going to contain a subspace. And we want to use that subspace for local correction. So we want to, so we now have an existential statement, which is that given an algorithm of this kind, there exists a subspace such that every vector in that subspace can be decomposed into 4 good instances. So for every input that comes from this subspace, I can now solve the problem, because I can break it down into a sum of 4 good instances. And because we're talking about linear problems, I now just apply alg to each one of these separately, combine them, and this will work with certainty because of the simplifying assumptions that I've made. But at this point, nothing is constructive. All of this is just existential. So how do we obtain this decomposition? So even if for a second, let's assume that the input just comes from V. Yeah, go on.
Why do you call them good?
Oh, because ALG succeeds on these instances. Yeah. So in this, so here I've made the simplifying assumption that ALG is a deterministic algorithm. More generally, it's the set of inputs on which ALG succeeds with some non-trivial success probability.
Like for fields, so you're looking at finite fields, right?
Yeah. But it does work for large enough fields, large fields as well. So in principle, okay. So Bogoliubov's lemma also works for any. No, in fact, it works for compact. I'm not okay. I think compact abelian groups. So it works in much more general sort of continuous spaces also.
Because for example, in Rn, right? Like
yeah.
That dimension, even if it's n-1,
yeah,
it does leave out pretty much everything.
Yeah. That's a good point.
Zero.
Yes, that's a good point. Yeah. So here we're only focusing on finite fields, vector spaces over finite fields. Okay. Yeah. So the idea is that we want to obtain. So for a second, if we assume that we're getting an input from the subspace V, even then we don't yet know how to obtain the decomposition, and then if we get inputs that are outside V, we have no idea what to do. So I see that I'm sort of running out of time. So I will not focus too much on the techniques, but I'll skip over some of the technical slides. So one of the things that we have to prove in this work is a probabilistic analog of Bogoliubov's lemma. And this is to deal with the way quantum algorithms are set up. So we have to prove that we had to prove something similar to Bogoliubov's lemma for dealing with, so quantum algorithms are sort of like probabilistic algorithms, but they're a little bit different because it's an L2 probability theory. And to deal with that, we had to prove this probabilistic version, a robust probabilistic version of Bogoliubov's lemma. We still don't know how to use it at this point. So we need to learn the subspace V. Somehow we need to learn some succinct description of the subspace V. We need to figure out how to sample from the set of good instances. Because if you recall, in the simple BLR idea, linear correction, what happens is that we pick a uniform random vector from the whole domain, and then we break up the arbitrary instance into R plus V minus R. What we now want to do is to break up the instance into things in X. So we want to be able to sample from the set of good inputs somehow. And I think this is related to the question you asked earlier. We also need to amplify the success probability. So what we get at first is just an algorithm alpha prime that succeeds with probability alpha or something that's polynomial in alpha. We also want to boost that up to arbitrary success probabilities. So these are the main things that we deal with. And in the following slides, I'll just give you a quick taste of what techniques we use to achieve this. In the classical setting, we don't yet know how to deal with any of these three questions within the complexity limits that we're given. So for linear problems, the limit is n squared. We have to solve each of these problems in little o of n squared complexity. In the classical setting, we don't yet know how to do any of these three things. And that's where quantum algorithms enter the picture. So there are some heavy quantum tools, some quantum algorithmic primitives that we were able to use to address those three red questions on the from 2 slides ago. So just to sort of give you an overview, there are 4 primary techniques that we're using, and they're all related to this this idea of implementing matrix functions. So given a matrix as input, you want to compute a function of that matrix. A simple function would be just given a matrix A, output A squared. But there could be more complicated functions, like you want to exponentiate a matrix, for example. So there are some very general quantum tools that are able to address this problem. There is something that is called fixed point amplitude amplification. This is related to Grover's search. So it's a version of the search algorithm that monotonically converges to the right answer. So again, these are fairly technical at this point. So I'll skip over the details. Another ingredient that we use is what are called singular value threshold projections. And finally, a key ingredient in making the whole thing constructive is Fourier sampling. So we need to be able to succinctly describe the Bogoliubov subspace V. And this succinct description is going to come in the form of its Fourier spectrum. We're going to be able to describe that subspace in terms of its orthogonal complement, which we obtain through Fourier sampling. Okay, so 3 quantum ingredients. I'll just quickly go over them. So one is matrix vector product verification. So one of the reasons why we can do this in the quantum setting is that we can verify matrix vector products faster than we can actually compute them. So classically, for matrix multiplication, there's something called the Frey-Waals algorithm, which allows you to verify matrix multiplication. So given 3 matrices, A, B, and C, the question is to ask if AB equals C. This is a verification problem. Frey-Waals algorithm solves this problem in big O of n squared complexity, n squared time. And matrix multiplication, as we know, has a lower bound of n squared, and the best upper bound is n to the omega for matrix multiplication time. So there's the gap between the upper bound and the verification time. Similarly, in the quantum setting for linear problems, for verifying a matrix vector product, we can do it faster than you can compute a matrix vector product. And we can also show that a classical algorithm requires omega of n squared time to verify a matrix vector product. So classically, there is no Frey-Waals algorithm for matrix vector product verification. And the idea here is that we can locally compute the matrix vector product. We can compute each entry of the matrix vector product locally, and then we can do a very subtle version of Grover search. So that's one of the key ingredients in our reduction. Second key ingredient is the ability to sample from this set X. So far, all I've been able to say is that there exists a certain set X that has has the property of being good. We then construct an algorithm that can sample from that set. And this algorithm is it's a version of Grover search. So it's rapid mixing of Markov chains. And yeah, these are some technical details that are not too important at the moment. And again, we can do this with gate complexity n to the 3/2, which is less than n squared. And that's the important thing. The third ingredient is Fourier sampling. So it's a version of the Goldreich-Levin algorithm. So you have some unknown function, and you want to sample from its Fourier spectrum. What that means is this function f has some Fourier transform. We want to sample a Fourier character with probability proportional to its Fourier coefficient, the square of its Fourier coefficient. So we extend that. There is already a quantum Goldreich-Levin algorithm from about a decade ago. And we extend this algorithm. It's based on the quantum Fourier transform. We extend it to the setting of noisy inputs. So in our algorithm, we're only able to obtain a noisy function as input. So there is some underlying function f, but we can't compute it exactly. We only have an oracle that's noisy and outputs f. So we extend the existing quantum Goldreich-Levin algorithm to this setting and show that it can still output characters with probability proportional to something that's close to the square of the Fourier coefficient. And this we can do in much better than even n to the 3/2 complexity. So these are the 3 key quantum ingredients, the key quantum algorithms that we use, and these exactly address the three questions that I put up here. So the Fourier sampling method lets us learn V. Sampling from X was the second algorithm. Amplifying success probabilities is a combination of using verification. So we solve the problem, verify if the solution was right, and then this somehow, this lets you amplify success probabilities. Exactly. Okay, that's a great question. So I'm going to come to that. I might maybe run 5 minutes over time, and I'll show you how that works. So putting it together. So this, just to remind you what the result was. We're given a unitary quantum algorithm that solves linear problems on average, and we're going to construct alt prime that solves all instances. So what do? If we're given an input V that's in X, then we just run the algorithm. There is a high success probability. We don't have to do anything further. If V comes from the set V, the subset V, the subspace V, then we can locally correct using Bogoliubov's lemma. We've now learned V. We have an explicit representation of V, so we can break the input little v down into 4 components in V, and we can solve the problem. And yeah, so these are this is essentially what I was talking about earlier. So we apply Bogoliubov's lemma to the to this subset of good instances. We get a subspace out of that, and then we can use quantum algorithm 2 to sample things from the good. Yeah.
You don't have this X constructively. You don't just
We can sample from it. We don't have X constructively, but we can sample from X. We have V constructively. We have an explicit description of V. Okay, so right, yeah, this is how we get an explicit description of V actually. So we consider the indicator function of the subset X, which we don't know, but we know it exists. And by doing some Fourier analysis on this indicator function, we can learn a basis for V. We can learn a basis and some other important things that go into the reduction. Right, and the reason we need to do that is related to your question, which is what happens if we get an input that's outside the Bogoliubov subspace V. So yeah, again, this is how linear correction works. So we break up the instance V into 4 pieces. And because of linearity, we can recombine the outputs of alg on those 4 pieces to get the solution. And there is some success probability for this to happen that depends on alpha. And then we can use the quantum verification algorithm plus rapid mixing of Markov chains to boost this success probability. But then now the important thing is, what happens if we get an instance that's not in V? So to begin with, X had density alpha. V is contained in 4X. V might be smaller than X in some sense. It might have density smaller than X even. So we haven't really gained anything in some sense. But the important thing is that V has structure. V is a subspace. So the idea is that we can tile the entire vector space with the subspace. So because we have a subspace, if it was just a subset X, it's not clear that we can tile we can reach all vectors in the space by just shifting points in X. But if we have a subspace V, there is enough structure that we can prove that by sampling a random shift, there is an appreciable probability of hitting every vector in the whole space. So if we draw, if the input to the algorithm, if the worst case input is some arbitrary vector V that's in some corner of the vector space Fn, there's this Bogoliubov subspace V sitting in some corner. So your input might not be in here, but we can sample a sparse input vector. So the sparsity S is the vector itself, but the sparsity of that vector is one of the things that we learn here. So when I said some additional useful information from Fourier sampling, from Fourier analysis of the indicator function, we learn something about the kind of sparse shift that's required to tile the entire space with the Bogoliubov subspace of X. So as this picture tries to illustrate, we randomly sample a sparse shift vector, push the Bogoliubov subspace there, and then we can prove that with some lower bound on the probability, which depends on alpha, we are going to hit arbitrary input instances. And this way we can hit all inputs in the entire vector space, and with the probability that depends on alpha, we can solve them, and then we can boost that to arbitrary 1 minus delta. So just to go back, we're interested in these reductions because they give us new ways to think about designing algorithms. So they give us new ways to get worst case upper bounds by obtaining average case upper bounds. And they also allow us to prove average case lower bounds from worst case lower bounds. So I just want to give a very quick example of an average case lower bound. I don't have a slide on this, so I'll just say this in words. For the quantum problem of matrix vector multiplication, there is a worst case lower bound of n squared. So it takes a circuit of size n squared to solve the matrix vector multiplication problem in the quantum case. And because we have a reduction now that has overhead n to the 3 halves, this means that even an average case quantum algorithm for the matrix vector multiplication problem continues to have the same n squared lower bound. So that's an average case hardness result that we prove in this work. So I think that's all I have to say today. Some open problems that are left by our work are, so we still don't know how to do this for classical algorithms. So classical algorithms for linear problems, given an average case algorithm, we don't know how to construct worst case algorithms out of that. And then can we extend the quantum reductions that we have to nonlinear problems? And what is an example of a nonlinear problem? Suppose you have inputs y and x, and you want to compute a quadratic function like that. Do our techniques extend to this setting? This is something we're thinking about at the moment. And there are a lot of other quantum input models out there. So I haven't really talked much about what the input model is here, but you can look at our paper for more details. We focus on a certain input model, and there are some other popular input models. And for those of you who are familiar with this, the HHL algorithm, this was a very famous algorithm that came out in 2009. It's the Harrow-Hassidim-Lloyd algorithm for matrix inversion. It made a big splash, and HHL problems, HHL type problems, by this I mean problems where the input model has a certain feature, it has a certain quantum feature. And we're also thinking about reductions for quantum algorithms in this input model at the moment. So thanks for listening. That's all I have to say today.
Are there any questions?
Yes.
Curious about one thing. You might have already covered this. So essentially, that lemma.
Yeah.
Sort of.
Yeah.
A set of space.
Yeah. Yeah.
So I'm curious about the actually 3.5 factor. Begin with x is a space of large.
Right.
End up with speech extractives or.
I see. Okay, that's a good question. So you're saying if there is more structure in the problem, so that the set of good instances is also structured. Okay, I'm not sure. We haven't really thought about that. It might be the case that you can get more efficient reductions if there's such a guarantee. Yeah.
Is the code that significantly crucial, or it's just influences union bound?
Yeah. The 4 just influences the union bound, and in our case, we could have used 3 also, but the analysis is more complicated, so we just use 4.
But it's not like it's easier for larger constants. Is it some of the other?
So there will be a trade-off in how many times you need to use alg versus that constant, because if you break it up into more instances, then you need to use alg more times. So you can either optimize for the number of times that you want to use alg or for the overhead of the reduction. But in principle, there might be some kind of trade-off between those two quantities, but we haven't really worked that out.
Intuition in finite complexity for commutative problem, let's say IISc or orthogonal vector or see some whatever problem that is important. Okay. I don't know if there can be mapped to linear problems or not, but
right.
Any intuition for commutative problems by these figures?
Okay. Again, that's a great question. I don't know. I'd love to talk about that later if you have any ideas. Yes.
So, the main theorem with this additional 2 of elements.
I see. So you're saying maybe if you allow a larger constant in the Bogoliubov lemma and use alg more times, can you reduce the gate complexity? Is that the question?
Or some other thing, yeah.
Okay, right. I don't know. We don't have a lower bound on the complexity of the reduction. It seems like, okay, there are maybe some tangential reasons to believe that this is optimal, which is that the ingredients that we use, the quantum algorithms that we use, especially the search algorithm, is optimal. It's known to be optimal. So I think my intuition is that this is probably close to optimal, but I don't know.
So those 4 quantum things that you use are essential for this thing to work.
Yes, they are. So even if we dropped one of those ingredients, the reduction would not. We don't know how to construct the reduction.
So this is a big question. So you said additive comparator sometimes useful from other things.
Yeah.
My question is that 4 from Bogoliubov lemma.
Yeah.
Is that purely related to the 4 squares theorem?
Oh.
Because 4 squares, 3 squares, 2 squares, these things keep dropping. Like
right.
Number.
Okay.
The amount of numbers you can reach with some of these squares keep dropping.
Yeah.
And there's some proof by Mikowski that uses.
Right. I'm not aware of any connection, but this problem Bogoliubov's lemma is also connected to the Erdős basis problem, so it might very well be the case. But I'm not aware of any connections. I'm not really an expert on the additive combinatorics part. We just use it as a tool.
That's a volumetric argument, and this is more dimensional.
Right. Yeah.
So that would be surprising.
Right. Mm-hmm.
The totality is coming to different things.
Okay.
Let's thank the speaker.
There is a question by Manish. He says that the fixed point amplitude amplification algorithm generally grows the size of circuit exponentially. How does it impact the output complexity in this work?
Okay, right. So the fixed point amplitude amplification, the place that we use it is I don't have any slides on this, but the place that we use fixed point amplitude amplification is when we want to verify the output of a quantum algorithm for a linear problem in superposition. So we have the quantum algorithm is outputting some state of which some component encodes the answer. And what we want to do is flag the component that contains the right answer, and then we boost the component that's flagged. So we can show that for our application, the number of rounds of fixed point amplitude amplification that we need to perform is square root of n. It grows to square root of n. So yeah, if that answers the question, in our application, that's the overhead that fixed point amplification incurs.
Are there any more questions? Let's